You know, there's a secret language all around us, in everything we see. It's the language of geometry. These are the hidden rules that shape our world, from a spider's web to a skyscraper. So let's go on a little journey and figure out how to speak it.
To get us started, here's a question for you. What on earth does a woven basket have in common with a honeycomb? I know, it sounds a little random, right? But the answer is the whole key. They're both just perfect examples of how super simple, repeating rules can create these beautiful, complex, and, well, in the case of the honeycomb, amazingly efficient patterns. All right, so let's start with maybe the most basic pattern idea there is, weaving. We're going to see how just taking a single thread, or in our case, just a simple strip of paper, and following one little rule over and over again can create something surprisingly strong and intricate. The process itself is, incredibly simple. The rule is basically just over and under. That's it. And by following that one alternating instruction, you start to see this strong, flat mat just appear out of a bunch of individual strips. It's really our first glimpse of how order can come from a simple, repeated action.
And that right there, that's our core concept. See, a pattern isn't just some pretty design, it's really a set of repeating rules. For our little mat, that simple over and under sequence is the rule that guarantees what we get in the end. It's basically predictability in action. And this is where things get really powerful, because once you get the rule, you can start to play with it. What if instead of 1 over 1 under, you made the rule 2 over 1 under? All of a sudden, a totally different, more complex design shows up. The complexity doesn't come from the paper. It comes from just a tiny little tweak to the rule itself. Okay, so let's take this idea and blow it up a bit. We've seen how rules can govern a single line in a weave. But what happens when we try to cover a whole surface? Well, that brings us to the puzzle of tiling, or if you want to be fancy, tessellation. Why is it that some shapes fit together perfectly, while others leave those really annoying, awkward gaps? Just think about any tiled floor you've ever seen. It's almost always made of squares, maybe some rectangles, but have you ever seen a floor tiled with pentagons? Five-sided shapes? Probably not. And there's a very real mathematical reason for that. They just don't fit together. It turns out there are only 3 regular polygons that can tile a flat surface all by themselves. You've got your triangles, your squares, and your hexagons. That's the list. Shapes like pentagons and octagons, they're always going to leave gaps, no matter which way you turn them. But why? The whole secret is in a single point, that corner where all the tiles meet up. So, if you're using squares, how many can you jam together around one point without any gaps or overlaps? Exactly 4. And the math is actually super simple. Each corner of a square is a perfect 90 degrees. You put 4 of them together, and you get a perfect 360-degree circle. It fills the space completely. So, does this whole 360-degree rule work for other shapes? What about equilateral triangles? Each of their corners is 60 degrees. So how many of those do you think we need? You got it, exactly 6. 6 of those 60-degree angles click together to make a perfect 360. Again, no gaps, no overlaps. It's a perfect fit. And what about our last one, the regular hexagon? Their corners are a lot wider. They're 120 degrees each. So how many of these is it going to take? Just 3. Their 120-degree angles also add up perfectly to 360. So this ability to tile isn't some kind of magic. It's a really strict mathematical rule. The corners have to meet up and form a perfect circle. What this all means is that shapes have these distinct, well, you could almost call them personalities, and they're defined by their properties. To really understand how they're going to behave in a pattern, we need to learn their language, the specific rules about their sides and angles that make them what they are. Take triangles, for example. In the triangle world, an equilateral is kind of the perfectionist. All its sides and angles are totally equal. An isosceles is more balanced, with 2 equal sides. Every name you see here, it's not just a label. It's really shorthand for a very specific set of rules that shape has to follow, no exceptions. Okay, so let's play a quick game. If a shape's rule is all my sides are equal, but my angles aren't, well, it's got to be a rhombus. What if the rule is all my angles are right angles, but my sides aren't all equal? That can only be a rectangle. See? Each description leads you to one and only one identity.
So, now that we've got a pretty good handle on 2D, let's build our way up into the third dimension. The exact same principles of rules and properties still apply, but this time they're going to create the solid objects that make up the world around us. Here's a classic puzzle to get you thinking in 3D. I want you to picture a Rubik's Cube. It's made of 27 smaller cubes, right? Now imagine you dip the whole thing in a bucket of paint, and then you break it all apart. How many of those little cubes will have paint on exactly one side? Just think about it for a sec. Okay, let's break it down. The 8 pieces on the corners, they get paint on 3 faces. The 12 pieces on the edges get 2 faces painted. The answer to our puzzle? It's the 6 cubes that are right in the center of each face. They're the only ones with exactly one side painted. And how cool is this? There's one single cube right in the very core that's completely untouched by paint. And this same logic applies to even really complex 3D shapes, which are called polyhedrons. An icosahedron is built from 20 equilateral triangles. A dodecahedron is made from 12 pentagons. Now, remember how pentagons totally failed at tiling a flat surface? Well, in 3D, their angles are actually perfect for folding up to create this beautiful enclosed solid. The rules just change depending on the dimension you're in.
So we've gone from a simple line to a flat plane, all the way to a 3D solid. Now it's time to bring it all home and see how this hidden geometry is, well, truly everywhere. Here it is, the big takeaway. These aren't just a bunch of abstract rules from a math book. From the pattern on your shirt, to the tiles on the kitchen floor, all the way to the incredible structure of a honeycomb or a skyscraper, this universal language of geometry is actively designing everything around us. We started by calling geometry a hidden language, but you know what? It's not so hidden for you anymore. Now you can see the rules, you get the properties. So the only question left is, what patterns are you going to discover next?